Hello all. Thank you for joining us in this webinar. I'm Kishan Joshi, the chair of Bell's San Francisco Bay Area chapter, and it gives me immense pleasure to continue bringing more power to 2022 with this webinar. Here's a little bit about our chapter. Recently, we were the recipients of the 2022 Santa Clara Valley Outstanding Chapter, 2017 Region 6 Outstanding Chapter, and the 2017 Bell's Best Chapter Award. Today's talk is on power electronics hardware design for manufacturability by Dr. Grant Pittel, CTO of Magna-Power Electronics. I would like to thank the support from our wonderful IEEE co-sponsors who help us spread the word around and help us in bringing forward these webinars. The Princeton, Central Jersey, Philadelphia Pels chapter, Santa Clara Valley section EPS chapter, and the Dallas Pels PES IES chapter. There's a lot of work that goes on in the background in organizing these events and bringing initiatives to our membership. And I'd like to thank the support from the excellent team of officers and volunteers from the Pels San Francisco Bay Area chapter. None of this would have been possible without their support. IEEE senior membership is the highest grade one can apply through either self-nomination or being nominated by others. There are a number of benefits like recognition, leadership, commendation letters, and others listed here. We can help you get the required recommendation. Please feel free to reach out to us. Also, do not forget to check out our new website for the info about current and past events. Slides and talks for a number of talks can be found in the archive section in the past meetings section. Also, you can follow us on Twitter at sfbac_pels for more updates. Before going ahead, I would also like to mention about our upcoming talk on disturbance-free BIST techniques for loop characterization of DC-DC converters and LDOs by Dr. Bertrand Bukloglu, Onsemi Endowed Professor at Arizona State University on October 27th, 11 a.m. to 12 p.m. Please feel free to register on our website using the link that will be made available soon. This is the remaining list of events planned for the year ahead on topics related to power electronics. If you'd like to be in loop on all the great talks and events happening, IEEE eGrid delivers all of that info down to your inbox for free twice a month. So be sure to register at the link shown here on egrid.biz. And thank you for being here. The PDF slides and the recording of the webinar will be uploaded to the archive section of our website, which you may refer later. Now, a little bit about our speaker today. Grant Pittel received the BS degree from Cornell University, where he concentrated on digital signal processing. He received the MS and PhD degrees from University of Illinois at Urbana-Champaign, with a research focus on digital control in power electronics and life cycle behavior of lithium-ion batteries. Before joining Magna-Power Electronics, Grant was a senior engineer at PC Krause and Associates and attended a 3-month internship at Google's platform division in Mountain View, California. He was a finalist in the 2002 Cornell Big Red Venture Business Idea Competition, received the IEEE IAS Myron Zucker Student Design Award in 2003, was a 2004 Energy Star Efficiency Challenge winner, and received the 2005 Granger Outstanding Power Engineer Award. He has written 5 first author publications and actively volunteers for the IAS and Pels chapters. He serves on multiple committees and is the past chairman of Industrial Power Converter Committee. Grant joined Magna-Power as Director of Engineering and later as Vice President of Engineering, where he was instrumental in creating the Magna-Load DC electronic load product load line, bringing digital control to Magna-Power, and developing an engineering workflow and review system to scale up the company's engineering team. Now, in the role of CTO, Grant oversees all engineering and software activities at Magna-Power, including new product development and internal company technologies. Without further ado, I would like to hand over the stage to Grant.
Thank you for the warm welcome, Kishan, and it was an honor that you invited me to give this talk today.
Looking good.
We're all good? Great. I guess even before I even go through the agenda, I just wanted to invite the audience. I really would like your feedback on this talk. Out of nowhere, I got invited to give this talk or a small modification of this talk to a larger audience. And I'm kind of, I really would like the additional feedback. Just make note of the slides, and I will provide my email at the end of this presentation so you can provide me feedback on things that worked and didn't work. During this talk, I'm going to give a quick introduction about our local chapter here on the East Coast and Magna-Power and its role in history and test and measurement. And in particular, and then this presentation really focuses about issues that maybe engineers don't know about when they go to production, and things they can do to help their designs get completed faster, and learning about how to deal with external manufacturing resources, and at Magna-Power learning how to deal with the internal manufacturing resources. And some specific things on design automation, and we do a lot of the different types of record keeping processes that we do here to make sure that prototypes run smoothly through the company. A quick introduction for those on the line that are joining us from the East Coast. We founded the Princeton Philadelphia Power Electronics Advancement Consortium, PEAK for short, in 2019. Bad timing right before COVID, but we've been keeping it going. We've been doing webinars thanks to Minji and the Adler Center, and we are planning to do a factory tour tomorrow. So if you're in the area, please join us. The first hour will be a tour of the factory. We're doing it at 4 o'clock, where the factory is still running. And then the next hour, we'll have a general meeting. We'll provide updates from our officers. When we originally signed up for the chapter, I think we were one of the few, if not only, I call it the joint chapter. So we're a joint IAS and Pell's chapter, a joint section, so Princeton and Philadelphia, and a joint region, which is Pennsylvania and New Jersey area. I did this because I want to make sure the chapter would be successful by trying to net the largest group of people possible. So for those who don't know who Magna-Power is, we're mostly known for our counter over-the-shelf programmable AC/DC power supplies. We design and make over 350,000 different combinations, and we ship it, and we build and ship around the world. So some of the things that, what makes us special is, all over the world, there's different line voltages, and power supplies will behave differently depending on the lines. Like probably one of the worst is Japan. They have like I have 100-volt input voltage, and you have to design all the way down to 10% below that. That's standard power supply practice. So we have to be testing down to 90 volts. And in terms of our output and current ratings, we go up to 10,000 volts and 10,000 amps. And we sell everything under the spectrum. And to kind of give you an idea, if you look on the, let's see, can you see my cursor, Brian? So on the left, yes, yep. So you can see, I'm doing a call out here to California, since you guys are in San Francisco. This is test equity. You can see that out of the 6,000 different power supplies listed on test equity, many of you shop there. I know I have for my test equipment needs. We account for 5,000 of those power supplies. And DigiKey, which I know all you engineers out there use, you can see if you go into Magna-Power, if you select the Magna-Power power supplies, we're almost around like 10% of power supplies listed on DigiKey. And our power supplies are rack mounted, so they find all sorts of applications all over the place. In automotive, we're all in the electric vehicle industry, chemical processes for water treatment, military. You see them a lot in radar applications. Many universities have our power supplies because they're programmable and use them in a lot of different applications. Renewables, so we have capacitorless output power supplies, which is used very heavily in the solar industry for certain tests, doing the short circuit test on the input of inverter. There's been a big influx of fusion research being funneled in, and we've been seeing a lot of sales in that. And we even do things as crazy as animal science. For some reason, our power supplies are really good at stunning fish. So I think there was a nature conservatory, they dropped some leads in the water and they do a population survey to see how much fish would float out. And they also use our product in fish packaging, where they basically make the frozen fish fillets. So if you're ever having a nice fish, you can think maybe the electrons in that fish somehow came from the Magna-Power supply. We also recently, we're getting into a lot more specialty electronics products and options like blocking diodes, high accuracy linear regulators. And, when you get up into 10,000 amps, where are you going to buy cables from? We're the only one making power at this level. So a lot of times the test measurements and the things we use to support testing here end up turning into products. And one of the things I like to do is I like to see, we're not always in the spotlight, but if you look carefully in various pictures and images and media, you'll see that we're kind of in the background. We're helping power that innovation. On the lower left, you can see that we're in the Natural Shrimp Incorporated. This is on their corporate website. You can see they've shoved in one of our power supplies in the side of their product. They're using it for farming shrimp. On the right, I was folding laundry the other day, watching Bloomberg on YouTube, and they were covering a topic at General Fusion. There's been some really major innovations there. You could see our product inside their racks. And then on the bottom right, you can see Biden. He was sitting in front of NREL, and behind him is a bunch of our products inside that cabinet. And then, this all wouldn't be possible without the Magna-Power team. Below in the center, you can see the whole team there from this year's holiday barbecue. So I'm just going to go really briefly through the history. This has been covered in a IAS magazine that we were invited to write. The company was originally founded in 1981. We got our start making SCR power supplies, and the first funding for the company came from an SBIR grant to make a solar inverter. Obviously, Magna-Power doesn't make solar inverters today. But what did come out of that SBR contract was the power supply used to test that inverter, and that was slowly developed into a product. And the product line started to evolve and grow, and basically it was all being funded through R&D contracts at Magna-Power. It wasn't around until around I guess, let's see, sorry. Probably like the 99 type of era, we started to really focus on our own products around 1999 to 2000s. And we really, before we were private labeling, so you would see somebody else's name on the product, but it was actually we were building it here in New Jersey. Eventually we moved over to IGBT, switching power supplies, and we started going into 1U and 2U power supplies. And most recently, and in 2013, we came up with a 1U power supply called the SL. And so this timeline is a little bit off because we're now in 2022. So when the article was written in 2016, we launched the Magna-Load, and what the Magna-Load was it was kind of a lower volume product. We sell a lot more power supplies to do loads, but this let us test we call it the Gen 2 platform. So this is an all digital platform that we've been working on to help speed testing and provide more flexibility to customers. And leading from 2016 onward, like I said, we've introduced other products that are actually using, from this platform, we're able to reconfigure. It's got like a main control board. So just like you build a computer, you can build different products using different board sets. And so we've launched a high precision, high stability linear regulator. This is being used in, I guess, particle accelerators. They need a very stable output over time. And then in this and we also launched the blocking diode module, where in a lot of applications for power supplies, if you're going to be hooking up to a battery, you need to put that blocking diode in the front, which a lot of customers can be a challenge, especially if you're dealing with high current and high voltage. So we provide them a separate, I think it's a 1U size device, where you hook the power supply into the blocking diodes, and the blocking diode has fan and some cooling in it and some very limited protections on it. And in this presentation, we're taking this 1U SL, and we've now ported it to the Gen 2 platform. So, and during the process of doing this, we redid all the boards, we re-looked at how we did all the engineering, and you're going to be seeing a lot of pictures and workflows that we've extracted from that design process. So before Magna-Power, a lot of the high power power supplies were custom designs. And the formula was pretty much you would find a power electronics engineering firm to do the work. It would take them about 1 to 2 years to design and test. And then once that was validated, they would outsource the manufacturing. What Magna-Power has done is we listen to our customers and we don't go into crazy small volume power supplies. We want to pick the ones that hit the largest demographic. And since we have so many different combinations, it's not physically possible to have a BOM for every single one of those combinations. So we've come up with we take heavy use of parameterization, where you put in a parameter and then it outputs, different BOMs, or you put in, different, like say output voltages, and say what types of options are possible in that product. And so we parameterize everything we can here at Magna-Power. We parameterize our BOMs, we parameterize our test routines, and we parameterize our drawings. And one of the ways we're able to do this is from the very early days, we're in the programmable power supply business. So being able to program something and, kind of goes hand in hand with software. And so early on, we invested a lot in custom software written in QBasic, Paradox, and Lotus 123. And we kept on iterating and improving that software, upgrading it to Excel. And now we've on like full-fledged programs and custom software. And we heavily use a lot of open source software here, because then we can tweak it and do whatever we want from that. And one of the, part of our business is, we want to provide a very low lead time. So we have all the manufacturing resources located here. There's very little that we outsource out of this company, because I'll call it the pre-COVID days, you could order a power supply. We were physically building it up and getting it to you in 2 weeks. We don't stock anything here. And that's because we just have too many different combinations to be stocked. And so, by being in the business for as long as we did, by insourcing all this stuff, it allows us to learn from our mistakes, iterate and improve and repeat. So, we try and keep our production volumes low so we constantly be improving the product. So again, with the 350,000 different combinations, we've developed and use a lot of custom software. And even recently, we've now come up with a rule parameter-based quoting. So if you go on our website, you can type in the input-output voltage combinations and options, and it will narrow down from that gigantic list what's allowed. And a little shout out, I don't know if they're here, our software team that helped us, Soul Space. If they're on the line, thank you. They've helped us develop this software that we can put on our website. And in the bottom corner, you can see a little analytics that we wrote. I wanted to show it because you can see who the #1 state is. And every time I walk in the morning, I see this chart in our lobby. And California has been consistently a #1 customer for us year in, year out. So, and given the volume and different types of power supplies you sell, it's also kind of indicative of where a lot of the power research is happening in the United States. So I figured I'd throw that slide in there for you guys. And so because we have such a short lead time, it's kind of frantic around here. We require a lot of from our planners and production and engineering to address any types of material shortages or missing drawings or problems in test the moment they happen. Otherwise, we're going to be late on that order. Since we sell so many different combinations, sometimes it's never been tested before, and you might run into a strange situation in test. Because we sell so many different types of combinations, you might have wrong compatibility. Because we've been in business for long, we have to still maintain the older products. And as I was saying with our website, and also with we switch over to our version control system, because our data sets are so huge. We really bring a lot of software to its knees. I know we work a lot with, we had to work with Atlassian, they're the creators of Jira and Bitbucket, because we moved all our engineering drawings over to the cloud, not by choice, they forced us to do it. And we were basically exceeding our size quota. And so they had to basically put in special exceptions for our company. And the same thing with when we were using, and the same thing when we were working with Soul Space. They basically, it was causing some performance issues, but they worked through the issues with us. Okay, so the meat of this talk was coming out of a magazine article that we did at the winter of last year. I want to acknowledge my my co-author, Adam, who's also my brother and CEO here at Magna-Power Electronics. He also helped me a lot with the preparation of this presentation. So if you see it, he helped, all the videos you see, he did all the recording and editing of them. And he also did a lot of formatting in this presentation. So if you see anything ugly, you can blame me. He did a great job putting this together. In the magazine article, we covered a lot about design constraints, and specifically for our industry, which is like dealing with very high current and high voltage. And what you'll find is, in the case of printed circuit boards, as you start going to extremes in current, the etching and masking process changes quite a bit. And you need to be aware of these when you're doing your board layouts. And also when you start dealing with, like up to 10, when you start reaching 1,000 volts and beyond, you need to pay very closely to your clearance rules and your creepage distances. And you always have to be keeping in mind when you're setting up your rules, what your line-to-line requirements are, your line-to-chassis, and all our power supplies have floating output, so you have to consider what type of spacing you need on all these. And something that's engineers will and as you're putting these constraints in, like a common thing that can happen, and I'll show you some videos of what I mean by these constraints, is that you'll over constrain your design. And so you might think you're addressing one constraint, but the other one's overriding the other one. And so you'll end up having, basically it'll pass right through your clearance that you had set up. And one thing to really, and one thing to keep in mind is, you want to make sure that when you put on your design rules for printed circuit board design, you leave them all on. I can't tell you how many times, even like seasoned engineers that have been doing this for a while, they'll turn off some of these design rules, or they might not be aware of, some of the issues that happen when it comes down to production. So in general, for our clearances, we follow IPC 221, and that's shown on the left-hand side here. And so these are, and you can see that for minimum clearances, it has a lot to do with where the traces are located, whether it's located on the top or internal layers, or if it's exposed copper or has a solder mask on it. These clearances, they vary by quite a bit, almost an order of magnitude. And so you need to be kind of mindful of what's going on in your circuit when this happens. And then in addition to that, there's creepage. So clearance is used to define when the arc happens, and then creepage is used to kind of define how long that arc will stay connected for. And that's why pollution degree is a problem. And in our business, we have just so many different applications. We just see so many different things all over the map, and what customers are doing with our product. And when we get stuff back for repair, it can be kind of shocking sometimes. And in the video being shown below, you'll see that that these clearances, that these design rules I'm telling you about are they've been programmed into this printed circuit board. So as you're tracing it, it's kind of preventing you from going in these no-go zones. And it's very important to try and use as many design rules as possible, because a lot of these, when you violate a design rule, sometimes it's not obvious. For example, you might have, let's say you have a 4-layer printed circuit board, and the top layer is high voltage, and you didn't provide any clearance rules. You might have an arc from the outside to the internal layer from the outside of the board. Another common thing you see is you have a multi-layer board and you drop a via down, right? You might not see that there's not enough spacing between that via that's being dropped down from one layer to the other in an internal layer. So you can get an arc internal to the printed circuit board. So definitely try and leverage, these are great tools. They will drastically reduce the errors that you have in production and reduce the number of revisions that you have to do to get the design out. And going through a validation on a printed circuit board is expensive, so trying to keep those down as low as possible is good. And at the end of the day, the IPC standard, it is a guideline. You never know, and I'll show you can see how dirty the printed circuit board is on the left, and on the right you can see you're probably wondering that was a gecko. The gecko somehow got inside of the product. Don't ask me how, but he got inside the product and he arced it. So I don't think there's any IPC rule on gecko in terms of pollution rules. So when you're working with your board house, again, be aware of the layer stack that you're using, and design rules are changing with every layer stack combination that you use. So a 1 ounce printed circuit board has a lot different design rules than a 4 ounce printed circuit board, and that's because the etching process is different, and the tolerances just aren't going to be as good. And you can see for like a 1 ounce, you can put a 5 mil minimum trace width, and for a 4 ounce, it's 15. So if you're trying to do, a complicated digital control board or something, trying to put it, these very fine pitch ICs you need to put in there to make it work aren't going to happen. Be aware of that. The way we've worked around this in the past and others is what you do is you do board stacking. So you can see underneath the video, there's a very high ounce printed circuit board, 4 ounce, and then we basically make little sockets, and we put other printed circuit boards where the denser logic is for doing all the controls. In the video, I'm showing, earlier in my career, I was told when you send the boards out, put a README in there, and that's changed. Our board houses say, don't send us a README because we're not going to look at it. So the general census, at least of our board house, and it's been quite a few board houses told us, is you want to put as much of the information about your design in the Gerbers themselves. So that includes your layer stack, which tells you the thickness of your core, the material of your core, and the copper thickness, and the solder mask, and the color. And board houses are just going to look at that. And the majority of boards they're made overseas, so that's part of the reason why you don't send a README anymore, is that people are going to have a hard time reading it. They can kind of look at these tables and know what to do. And also, if you want your prototype in quickly, you got to be aware. You got to watch out for the Chinese New Year. I think that pretty much shuts down China for at least 3 weeks, and no printed circuit boards are coming out of China during those time of the years. We usually we work with a local supplier. Before sending out your designs, always run a DFM check. These are built into your design software. Oftentimes, when you send it out to the board house, they have their own DFM. That's designed for manufacturability, and they will send emails back and forth. Be inquisitive, keep on asking questions with your board house, keep a good dialogue going, because they are very knowledgeable. They know what's going on, and they can basically help you improve your design rules. And while it might take a little bit of time to program those into your design tool, it will save you a lot of mistakes and time in the long run. So now I'm going to go over some of the issues when you're doing your board layouts, things you see in particular with high power designs, and things I've seen a lot of things I'm often correcting. The first one is called the solder mask sliver. What a solder mask is it's like almost kind of like a enamel that gets put on top of the copper, and it prevents solder from flowing around. So if you look in the images on the right, you can see in the top right image, the solder mask, which is in the light green color, and then the exposed copper, which is the gold. And there was a little piece of mask separating those two joints. However, when you look at the black printed circuit board below that, that solder mask is gone, because what happened is the design rule was turned off for this and we missed it. And board houses basically will remove this when they go to build the board. And the problem with a solder sliver, looking down below that to the red printed circuit board, is that it will wick solder away from the joint. In the case of, and what that will does, it makes a bad joint, and it also will cause the automated optical inspection machine to flag that as a failure. Somebody in production has to go in and touch it up, and this all slows things down a lot and will cost you a lot of money. And also, if you're not careful, it can also cause bridging. You can see that capacitor on the right, even though it's basically sucking all the solder away from that pad, and it's not making a very good joint. So another, oops, excuse me. And then just to be aware, so when you do your board layouts, there's 3 different ways that the components will be soldered on. There's your traditional soldering iron, which you're familiar with. There's wave solder, where the board is floating across a bath of molten solder. There's reflow oven, which is typical with most production today, where it goes through an oven and the paste gets melted. And then the newer technology is called selective solder, where it's almost a kind of like a programmable robot solder pot that goes around and does each joint individually. And you have to be aware, so in order to get a good solder joint, you need to make sure that you have the right amount of heat going to it. And a common mistake I see in power designs is when they're putting a through-hole component, they will do a complete fill on that joint. And if you look on the bottom left-hand corner, you can see, and the picture next to it, I have a very large copper bus bar that's being soldered to this printed circuit board. And so and what's added, you can see there's little lines coming into the pad out to the copper pour. And so what this does is this kind of lowers the, that raises the thermal resistance of this joint. So it's not sucking all the heat away from the joint. And yes, you're probably wondering, well, isn't it better to use as much copper as possible? That way you get the most amount of conduction. And the answer is, well, think about it. Well, so some devices are only 20 amps. Do you really need a direct connection to an entire pour? And you might have seen this phenomena before. If you take a really low wattage soldering iron and you try and solder one of these type of joints that have been connected directly to, let's say, a 4-ounce core, what happens is the soldering iron will drop in temperature and it will get stuck to the joint. The soldering iron will physically get stuck to the joint because because all the heat is getting sucked out of that soldering iron, going into that copper pour, and it's unable to heat up that joint enough to get it a good melt. So be aware of the device ratings you're using, and use thermal reliefs to make production possible. And next, and if you look at the blue printed circuit board on the right, on the joint to the second, you can see kind of what happens. This is an example of a joint that does a direct connection to copper, and you see you're not getting a good fillet on that joint. So that results in a higher rate of failure of the device. It could get cracked, and it also that also would get flagged by inspection. So there we go. Time here. So now I'm going to go over some of the things we do to boards, and you should be doing too, to help the board move through production quickly. So like I said, we've purchased a lot of the equipment required to make the products here. So a lot of this stuff is just, we were completely ignorant to it about 10 years ago, and as we started buying in this equipment, we started altering our design so that we can leverage it to the highest degree possible. One thing to be aware about is the fiducial. So on a printed circuit board, and even on other automated assemblies, not necessarily PCBs, you need some sort of pattern on the item so that the cameras can align to it. In the case of printed circuit boards, the fiducial is used to align the paste stencil with the printed circuit board. So right before the stencil goes down to the printed circuit board for pasting, there's a camera in there that's shifting that stencil around to make sure it all the pads are aligning with the aperture openings on the stencil. In the case of the pick and place machine, the camera is scanning the fiducials to find basic center points, so that way it can paste the components very accurately. And typically when you put the fiducials around, you want to get it pretty well distributed on your design, because you might have warpage on the PCB, so it's good to get a good sampling of different measurement points. So you also need to be thinking about how this material is going to be floating around the factory. A lot of today, a lot of it's going to be happening on through conveyors. So on our printed circuit boards, and we provide basically handling for the rails. It gets clamped on, so make sure you don't have components too close to the edge, although get crushed. Make sure your printed circuit boards aren't too long across the conveyor, otherwise it flexes and it will cause what's called bounce back. And when you do that, let's say a printed circuit board is going through, is being placed, that there's a spring back once the head goes down and comes up, and it'll shoot the component right off the printed circuit board. And then when you go to depaneling, if you have the components too close to the edge, like we'll see on the right, you'll see it'll cause too much pressure on the PCB. It'll cause bending, and it will crack the components on it. Another thing to look out for is there's sensors and lasers to make sure when to stop printed circuit boards and other assemblies on conveyors. So watch out for that leading edge, because the laser needs to cross across it to prevent it. So sometimes we might have an opening or a gap, and it'll just completely pass through the conveyor and keep on running through. So I'm now moving on to how we manage prototypes. Because when you have 360,000 different combinations, you can imagine we're doing prototypes pretty much nonstop. Anytime there's we need to put a substitution part in, or we're working on a new type of option for customers, we want to put it through. We will do a prototype of it, validate it, and then we'll activate that BOM. And the important part is, when we do a prototype, we're trying to get all the records as close as possible as an actual production product. And the reason why is you want to kind of piggyback on production to have them do all the prototyping for you. You don't want to be in the lab hand soldering components on. If you provide them a schematic, a layout, pick and place file, they can just push this through right production. And I was on a phone call recently. If all the moons align, and if I can place an order on for a printed circuit board on Friday, they will make it overnight in China. I'll get the board in hand Monday. I can send it out to production, and then I can actually have a working prototype by Tuesday. And so to make this work, it requires like a lot of careful management of your records, making sure you have the BOM, and you also have to make sure that this prototype is somehow raised to the top of the work queue as high as possible. And we do this by adding special colors to the router instructions, giving it special states. If it's in pending state, that's a particular assembly will go through active, pending, and inactive. So a prototype is a pending bill of material, and that gets flagged in the system. And also when it's pending and when it has this crazy color ticket holder, it lets production know that they should be paying extra close attention to this particular job, because engineers aren't perfect. They'll make mistakes, and they'll work and they'll try and get it through. And when we do prototypes, we try to buy the parts as quickly as possible. We'll always do 1 or 2 day turns on it. And like I said, you have to bring everything to production, and you want to bring everything to as near ready production state as possible. So once with all these different models and bill of materials and items that we stock here, it generates a lot of data. And the important thing that we do is try and centralize everything to a single location. And this allows us to do sophisticated database queries, both for production, sales, and engineering. And once we have a central database, we can expose this information to other design software. If you look at the image below, you can see this is our schematic software. We're dragging in a resistor, but on the right-hand side, you can see this is a database containing all our resistors. And as an engineer, right, you want to use the resistor that's been vetted and that we have inventory of. And by having sophisticated reporting and data, it allows us to do volume pricing on part orders. We can reduce the amount of vetting we have to do to our vendors. It makes kitting simplifying, and also by having less components on the production line, they don't have to retool, and they can optimize the pick lines for that particular job. So from the software world, a lot of the things we do in the electrical engineering and mechanical engineering, we adopted from the software world. We have issue tracking systems, so somebody will report an issue that you have to state clearly how you repeat the issue, and that issue will stay in the system until it's resolved. And so this helps somebody from dropping the ball on important things that are happening. And more importantly, it provides a track record. So if the issue pops up again, we have a written record on what it was. It provides full visibility at the company. And on the left-hand side, you can see an example of what happens is an engineer will make a change on a drawing. He'll check it in, and then he's going to basically link that change to the issue that caused it. And now we have complete traceability in terms of the problem and the solution. And then we even have this tied into other software like our chat clients that's giving all our team updates on particular problems that are happening at the company. Firmware and software compatibility. So with all the different products and models, it's becoming a greater and greater challenge. When you launch your product, you have to make sure to provide firmware flashing. And the reason being is it allows you to address problems after you ship. So as a customer might call in for support, you can go ahead and issue a firmware update so that they can get up and running again on their line. And the challenges of firmware is that it's constantly improving. So the firmware, the hardware, and the software features are constantly being added. And you somehow have to manage how the boards can continue to communicate, even though the protocols change. And EEPROM settings need to somehow be revised based on these changes. And in the case, we have multiple chips per product, so we need to do multi-chip production product flashing, which is difficult. And you have to make sure that as you release new firmware, that it's going to be compatible for future features you plan on adding, and it's still got to work with the stuff you released in the past. Right now, we've got I think 3 or 4 different products on the Gen 2 platform, and I think we've only had 1 compatibility break. And so what that means is there's a situation, usually low level, where we're blocking the upgrade on flash, and usually that will have to come back for the factory for the control board to be updated. And you can see on the bottom, I've taken we call them snapshots. So this kind of explains the complexity of what we're dealing with here, where when we do a snapshot release, we're looking at all the boards that are related to that piece of firmware at that point in time and the changes that happened. And this allows us to look back in time saying, okay, back in 2019, these were the board sets that were being used with this snapshot. And that snapshot gets saved with the product when it goes out the door. All right, so when you design for test, all right, I'm going to skip through these really quick. So when you're doing tests, you need to consider where these test points can be accessed. Usually LEDs for us work really well. You can see in the video here, what I've done is we have all our printed circuit boards. They're very complicated pieces of software. So we have Morse code coming out through them, so you can tell at which state the firmware is having an issue. And this makes it really easy for testing to relay the information over the engineering. And for testing, because we sell, just like our quoting system needs to be configurable, our testing needs to be configurable too. So based on the type of product that's ordered and the options, certain things need to be tested out before it goes out the door. And so we developed our own testing, object-oriented testing, where based on the product, it will basically each tester team is different. If if it detects a major change in firmware or hardware, it'll actually add in a whole bunch of additional validations to make sure nothing else was broken, because it's really important to catch these things before it reaches the customer. We use version control here at Magna-Power. This is a lot more common in the software industry, but by doing so, it allows us to work in parallel, and every change is accounted for. We can go back. It also acts as a way to back up our information. And it's also a starting point for sharing that information in our bill of materials and being able to do differences. So in the case of programming, like the code difference is really important. It shows you which lines of code change. On the left, a lot of design software now has like basically drawing diffs. And you can see where a component changed in the case of this board layout, or in the case of if it was like a mechanical drawing, you can see where holes have gotten moved. And so recently, Magna-Power, we've recently moved over to solid modeling. This has been a great help to the team because it allows us to check form and fit before we even build it up. And as a result, in this and all the tools that I described earlier, it really has boosted the efficiency of the team. And just like I was telling you about configurability, our drawings need to be configurable, because you don't want to have a 360,000 different drawings for all the things you build. So we make sure that we're taking full advantage of any type of configurations in the design software. If you look at the video, you can see a zoom in of our new SLX, and we kind of are switching through different combinations of the output stage. And as a result of us moving to solid modeling, we've now been able to provide the production assembly drawings. Before, it used to be very expensive to put together an assembly drawing. In the past, we would have just provided some pictures from past designs. But over time, we've been able to develop models, build libraries, and provide. And so it's not as laborious to do anymore. So we're starting to do it more. And as you go through a production run, be very conservative with your revision statuses. When you make it active, it means you're ready for production. So we try and keep things pending as much as we can. Again, thank you. Sorry for going over a little bit. I'm looking for critical feedback. This is my email. And also below is information about the factory tour, should those who are in the area want to attend. And I just want to thank you guys. And if there's I open it up to questions.
Thank you, Grant, for a wonderful talk. I'm sure the audience will agree that this has been a very illuminating talk for them. We'll now go to the Q&A. So let me go over the first question. Since validation could be expensive, do you employ formal verification? What are your suggestions for mass production? How do you recommend to reduce the faults at different levels?
Can you state the question again? My hearing is terrible.
Yeah, since validation could be expensive, do you employ formal verification? What are your suggestions for mass production and to reduce the faults at different levels?
Right. So for the way we do it is I showed you we have very sophisticated testing. So a lot of times so there's a difference between doing a validation. If you're doing, let's say, a revision on a printed circuit board, the testing routine's already written up for that. So what we do in the case of validation of a standard board, let's say we're deciding to raise the power 10%. We'll make a small tweak to our test routine, we'll issue it, and then we'll push it through production. And then they'll test out that board, and then in that board, it's like, okay, let's put this into a customer unit. And then we'll see if that passes standard testing. And if all these things happen and it passes all the tests, we'll go ahead and activate that bomb. And for us, that's the way we save money, is that product was already going to a customer anyway, right? And if it passes standard tests, that's our criteria for it being allowed. So by validating it against a customer unit, you're basically saving yourself test time, because you had to test it anyway.
Right. Okay.
So that's how we say. That's how, at least for our products, that's how we can make so many different versions and not spend a fortune on validation.
All right. Yeah. Thank you. So the next question is: do you use selective soldering for through-hole components? Do you use tools-based constraint for that, or handle this manually? What tool do you use for board design?
Okay. Yes, we use selective solder here. I've known some manufacturers they're going to 100% selective solder. We still have reflow, wave, and selective. We use mostly selective for those really hard to reach areas. In terms of do I implement, I have not yet had any, production has never reported any issues with selective solder in our designs. And it probably has mostly to do with the fact that we use it very sparingly. We usually use it only on double-sided boards. Because in terms of, for board design software, I've used it all. At Magna-Power, we use Altium, but in my career, I've used AutoCAD, I've used Eagle, I've used OrCAD, and I've used like PCB Express when I was like, a student. So they're pretty much all the same, although Altium, I have to say, has been my favorite so far.
All right, thank you for that. Can you suggest an application note, reference documentation, or textbook where it covers the essential layout rules and provides guidelines on addressing EMI issues while designing high power supplies?
No, I don't have one. I'm sorry. This has been, I've not seen a good resource for that.
Oh, yeah, okay. Yeah.
And unfortunately, like if you look at layouts, like a lot of it is for digital electronics. And I can tell you when I did my internship many years ago, they were doing like 12-layer CPU motherboards, which if you look at that, your head spins. So, and honestly, the complexity of layout, there's a lot in doing the digital electronics. And in terms of, for us, like I said, we just follow the IPC guidelines on clearances and creepages, and we set up our rules accordingly.
Sure, okay.
Hey, Grant, though, this is Brian. I would like to highlight, though, that you did mention you put out some very useful articles recently, and I believe those also had a lot of the reference you referred to, the guidance, as well as the references that went along with it. So don't sell yourself short. You've already done it.
Yes, well, we did, like I said, the contents of this talk were covered in that magazine article we did for Pels last year. So if you're an IEEE member out there, Pels or IES, you get free access to these magazines. So definitely go to your IEEE Explorer and you can download it for free if you're a chapter member.
Right, yep. Thank you for that. Could you please elaborate on the snapshot process and how a snapshot would be helpful at some later date?
So what we do here is the snapshot allows us, so let's see how this is very complicated stuff. Well, let me see how I explain it. Over the course of time, a printed circuit, let's say you have a processor with 64 general purpose IOs and you decide to swap the pins on one of them. Okay.
Mm-hmm.
How do you do a firmware update and don't completely mess up your entire designs that you've done in the past? So we have something that's called software configurations that when we go to flash, when we originally do tests, we flash that hardware revision of that printed circuit board at that point in time. So for example, let's say 25750, that's the item number for the printed circuit boards being made, and R7 was the revision. We know with R7, the general purpose IO pone was here, and then we went to revision 8, it changed over there. So in our firmware, we look for those hardware revisions, right? And we'll make a change in our, we'll make a change in the firmware to redirect information from one pin to another. All right. So this is some pretty complicated stuff. So and now let's say in a snapshot, you can be doing this multiple places on multiple boards, very complicated. So the snapshot is kind of a way, it's like, okay, in March of last year, pretty much all the hardware, this is where we were in this point of time. And when we do is we use this for doing compatibility checking.
Mm-hmm.
So we know that, if you're doing firmware upgrades, you have to update the firmware. Let's just do another example. This is a snapshot of hardware. Let's say it's a case of software. We have our Magna Control UI right there shown on the screen in blue. Let's say you downloaded the software front end, it's on snapshot 7, but your hardware is on snapshot 6. Right? It can't talk to one another. So our software is going to know this and say, hey, you need to either downgrade your software and go to version 6 of the snapshot, or you need to upgrade your firmware so you can go to the latest firmware.
Right.
So basically, a snapshot is really just a way to kind of group all the changes together under
Right.
one roof.
Sure.
Complicated. I am sorry. That's like almost an entire talk altogether. I apologize.
Yeah, no problem. Thank you. So the next question is, are you using HIL simulation before manufacturing, and which software do you use?
Using what type of simulation?
HIL?
Say again.
HIL?
Hardware in the loop.
Right.
So we don't use hardware in the loop simulation, but our firmware is not, all of it is auto code generated. So when we were doing our original prototypes for the Gen 2 platform, we were doing hardware in the loop prototypes for that. And then we took all that code and we're using that as our production firmware code.
All right. Okay.
And a lot of times what we'll do is sometimes rather than putting a whole power supply on there, we'll put the power supply model in our firmware and we can test stuff a lot easily at our test bench.
Mhm.
So yeah, we do use hardware in the loop. Just we do it kind of grassroots though, where we're doing it directly in our firmware C code.
Right. Sure. Okay. And
again, that's a whole other topic altogether. Another talk.
Right. Yeah. Just one last question. I mean, we are running out of time, so I'll go through one more question, and then audience can follow up with you if they have more questions.
Yep.
Do you have a preferred approach for PCB sourcing for development versus production? For example, use a low volume domestic supplier until a specific level of design maturity is achieved, and then move to a production oriented supplier.
So I flip-flopped on this probably in the last 2 years. I found a really quick turn, low cost supplier. That was the one I was telling you. They're open on the weekends, and I can order boards and bring it in. Mm-hmm. However, their quality isn't very good, and their volume pricing is worse. So even though you're doing really well getting it in early, it's more expensive once you go to production. And another gotcha is if you validate it with the low cost, high speed one, and you decide to switch vendors, guess what? You're going to have to validate the design all over again because they're going to process those Gerber files differently. Mm-hmm. I can't tell you how many, just because you built it once with one vendor doesn't mean it's going to work with another vendor. They will mess that production up. Now I've seen that multiple times where purchasing will switch a vendor. Like it's now a requirement that purchasing is not allowed to switch a PC vendor. And if they do, it requires revalidation of the entire PCB, which is expensive, which is why I now say, go with the basically go whoever you're going to be using for mass production, even if you got to pay an arm and leg for it.
Right. Okay. Yeah, that's good info. Thank you. Yeah, thank you so much. This was, I mean, we do have a few more questions, but since we are out of time, I'd like to request the audience to contact Grant directly for the questions. Brian, did you want to add any comments?
Yeah, just before we have our closing comments, and thanks a lot, Grant. That was fantastic. I just want to highlight something for everyone. As even for some of you might have been attending this thinking, hey, well, this is more like, usually we give a more focused technical talk or whatever. This seems like just stuff about Magna-Power. I just want to highlight that this goes beyond that, and that's the real, the true value here. And I'm someone I've worked on, all sides in the power electronics world as, vendor, OEM, seen a lot of this manufacturing. And what's amazing about it is that the processes and stuff and the evolution that Grant described is truly just very differentiating and unique and special in the power electronics manufacturing industry and all that. And so I just wanted to make that comment so people realize this isn't just a Magna-Power fluff thing, but what these guys have done here really kind of sets a bar in so many different areas, from design and development to manufacturing. And so I don't just want to brown nose our speaker, but just to highlight that for folks to realize that there is something special here in what they do and all that. So Thanks again, Grant, for giving that talk, and thanks, Keyshawn, for letting me speak.
If you don't mind, Keyshawn, can I just say one more thing?
Sure. Go ahead.
Again, I just want to ask the audience, please send me in your feedback. I was invited to give a much larger talk to a much larger audience. The current drafted title for this talk will be idea, prototype, and production, shortening the gaps with manufacturable designs and software tools. So if there's anything in the talk that you thought really resonated with you, please let me know. Again, credit to Brian. If you feel like it was too, rah Magna Power, let me know, saying it needs to be more general. Maybe you felt my comments about the crispy gecko was inappropriate, and I'd love to hear your feedback on that.
Thank you. Thank you so much, Brent, for your time and for giving this wonderful webinar. And I'd also like to thank our sponsors, our co-sponsors, for helping support this webinar and helping make this webinar a success. And last but not least, I'd like to thank all the audience members for joining in on this webinar, and hope to see you all in our next webinar series. Thank you and have a good one.